Okay, students, now we'll see about the shear force diagram and bending moment diagram of an overhanging beam. Now here you have a beam ABCD which have overhangs beyond B and beyond C, overhanging to both sides of the supports B and C. So you can see here this beam is symmetric about the centroidal axis. So you can write the support reactions like this. Support reactions are P equal to RC equal to total load divided by 2, because this beam is symmetric about this vertical axis, centroidal axis. That is, the loading is symmetric and geometry also symmetric. And you can see this total load is shared by these two supports. Since there is no inclined loads and horizontal loads, there is no horizontal reaction at this hinge support. So you have two reactions, vertical reactions RB and RC. What is the total load? Total span length of the beam is 6 meter. Total load is 30 kilonewton per meter. So for 6 meter it is equal to 30 into 6. So the support reaction will be sharing the total load equally. So you can write the support reaction as 30 into 6 divided by 2. So you will get RB equal to RC equal to 90 kilonewton. Now we can write here RB equal to 90 kilonewton and RC equal to 90 kilonewton. Load is 30 kilonewton per meter. Now we have to draw the shear force diagram. In order to draw the shear force, let us take a section line at a distance small x from the left point A. Now what is the shear force at this section? Shear force at x-axis is equal to this unbalanced vertical force to the left of the section. So what is the unbalanced vertical force? Our sign convention is right downwards is positive. So left downwards is negative. So here the unbalanced force is the load for this midsection X. So this is acting downwards. So we can write here minus. This load is 30 kilonewton per meter. So for X distance it is minus 30 into X. Now we can find out what is the shear force at X equal to 0. That is, shear force at A is equal to 0. Now we can find out what is the shear force at X equal to 1.243 meter. That is shear force at B, which is equal to minus 30 into 1.243. So this is equal to minus 37.29 kilonewton. So we can complete the shear force diagram for this much portion. First of all, you have to draw the baseline, which represents the centroidal axis of the beam, of this overhanging beam. Now you have got the shear force at this point as 0. Shear force at A is 0 and shear force at B is 37.29. So let us mark this point here, 37.29. Now here you can see it is UDL, so the variation is linear. So we can join the point like this. So you have got the shear force for the portion AB. Now simultaneously we can write the equation for bending moment for this much portion. So what is the equation for bending moment? Bending moment diagram for portion AB. So let us consider the same section line x6 at a distance small x from A. Bending moment at x equal to bending moment due to this much load. This load is 30 kilonewton per meter. So for x distance, the bending moment is load for x distance is 30 into x into, it will be acting at the center of this portion, that is at x by 2 from this section line. So when you take moment about this section line xx, it is 30 into x by 2, which is equal to 30x square by 2. Now we can find out what is bending moment at x equal to 0, that is bending moment at a. By substituting x equal to 0, you will get bending moment at a equal to 0. Now we can find out what is bending moment at b, that is at x equal to 1.243 meter. So 30 by 2 into 1.243 the whole square. So you get bending moment is equal to minus, now what is our sign concept for bending moment? Sign convention is left clockwise is positive. So actually this is trying to rotate this moment and about the section line in the anti-clockwise direction. So our sign concept is left anti-clockwise is negative. So this is minus. So you'll get the value as minus 23.176 kilonewton meter. Now we can complete you can draw the bending moment diagram also. So first step is you have to project these important points downwards. Now we can draw the baseline, which represents the centroidal axis of this beam. So you have got this value, bending moment at A is 0 and bending moment at B is equal to 23.176 kilonewton meter. So actually this is a UDL, so the variation is parabolic. So you can draw this parabola connecting the points A and B. So this is 23.176 kilonewton meter. Now let us consider another section line measuring x from A and considering all the left hand side forces. So we can write the equation for shear force at the section x1 at a distance small x from point A as what are the unbalanced vertical forces. So all the forces to the right of the section downwards is positive. So the left of the section downwards is negative and upwards is positive. So here you have RB acting upwards. So upwards is positive, left upwards. So it is plus RB minus the load for the sponge portion x distance. It is acting downwards, so it is negative minus 30 into x. So value of RB is 90 kilonewton minus 30x. Now at x equal to 0, what is the shear force? At x equal to 0, you have already obtained the shear force. So we need to find out what is the shear force at x equal to 1 point. At x equal to 1.243, what is the shear force? So substituting in this equation, you get shear force at B is equal to B minus 30 into 1.243, which is equal to 52.71 kilonewton. So you have got this value as plus, which means that in the shear force diagram, at this point B, it becomes positive and the value is 52.71. So let this be the point. Now we can find out at what is the bending moment at this point? Is there any change for bending moment at this point? What is the equation for bending moment at this section? That is at x1. What is the bending moment? Bending moment at x1 is equal to, this distance is 1.243. So we can write the remaining distance, this much, is equal to x minus 1.243. RV about this section x1 is R to x minus 1.243. Now sign convention is left clockwise is positive. So we can write plus 90 into x minus 1.243. Now what is the moment of this much load? 30 kilonewton for a distance x. It is left anti-clockwise minus. So minus 30 into x square by 2. Now we can find out what is bending moment at x equal to 1.243. So m at B is equal to minus 15 into x square, 1.243 the whole square, plus 90 into 0. So this is equal to minus 15 into 1.243 the whole square, which is minus 23.176 kilonewton meter. So we can draw the bending moment diagram. And this value is same what we have got in the previous case. So now we can find out what is the bending moment at x equal to 3 meter. At x equal to 3 meter, bending moment is equal to 90 into 3 minus 1.243 minus 15 into 3 square. So this value will get it as 23.13 kilonewton meter. So x equal to 3 meter from A, you have got the bending moment as 23.13 kilonewton meter. So at x equal to 3 meter, you get the shear force as 0 by substituting in this equation, which means that the shear force diagram is like this. So for the right half, it is symmetric, and we can draw it similar to the left half. So since the equation for bending moment varies with x, you can say the variation of bending moment is parabolic. The bending moment diagram is parabolic. So you can draw the bending moment diagram like this, and you can find out what is the point of contraflexure. That is the point at which the bending moment crosses the x-axis by equating the equation for bending moment for this section to 0. That is this equation to 0. So you get, by equating this equation to 0, you will get the point of contraflexure x equal to 1.758 meter. So this distance is 1.758 meter. So the equation is 90 into x minus 1.243 minus 15 x square equal to 0. By solving this equation, you will get x equal to 1.758 meter. So this is the bending moment diagram, and this is the shear force diagram. So the right half will be symmetric to the left half. Okay, thank you.